I said that everything, in some sense, that was done for centuries after Newton was filling in the details to F equals ma. I don't want to give you the wrong impression. There are a lot of fascinating details. Newton's universe is rich and wonderful, and centuries of work by many, many, many brilliant people went into producing insights and understandings, and I wish I had the time to tell you about at least that part of it that I know. But we're in an astronomy class. What I'm going to do is give you sort of a highlight reel of those of the aspects of what has been learned that will impact what we do and that we will need, and we will go through and try to develop, if not as deep an understanding as we did for gravity, which will be central, some intuition and some understanding for some other important concepts in physics. And as I said, we'll organize it by the M, the structure of matter, and the F, the forces that act. And we will start with the M side. We'll start with what we know about the end of the 19th century about the structure of matter. By the end of the 19th century, we have a pretty comprehensive understanding of the structure of matter, and its center is what is known as the atomic theory of matter. All known matter is made up of 100 or so types of atoms, immutable units. They're indexed by a number called Z that runs from 1 to whatever, 100, and roughly elements with higher Z have heavier atoms, more massive atoms, and these characterize the chemical elements. We understand some rules by which they bind together to form compounds and molecules and various kinds of objects. And bulk matter can appear in one of three common states. We have solids, we have liquids, and gases. And in each, the bulk properties are understood as a consequence of the microscopic dynamics of the atoms and the molecules that form it. And as a good and very helpful to us example, one of the forms of energy we discussed when we talked about non-conservation of mechanical energy was heat. Friction, for example, converts kinetic energy to heat, and heat causes an object's temperature to rise. So we know what we mean when something is hot. We mean it has a high temperature. In the context of an atomic theory, we have a good understanding of temperature. Temperature is simply a measure of the average random motions of atoms and molecules inside an object, which explains why heat is sort of the lowest common denominator of energy. Heat is the energy that something has when it's doing its own thing. It's not moving in bulk, but its own internal degrees of freedom are randomly fluctuating. And for example, in an ideal gas, that's a gas that's made up of atoms or molecules that have no internal degrees of freedom and are just non-interacting and bumping off each other in the walls, then you can show that temperature gives you the average kinetic energy of a molecule or an atom or whatever it is proportional to the temperature. And temperature in this expression is measured in Kelvin. Kelvin degrees are the same as centigrade degrees. That just determines the units in which we measure this constant here, K, which is called Boltzmann's constant. What is not arbitrary, of course, is where you put the zero of T, because doubling the temperature relative to that zero involves doubling the energy, and there is a temperature at which the average kinetic energy of molecules descends to complete zero. This is absolute zero, or negative 273 or so degrees centigrade, and this is the origin of that. And using these equations, you can see that at higher temperatures, the molecules bump around more. A gas exerts a pressure on any container in which you put it. The pressure is a force per unit area applied equally in all directions, and the pressure times the volume for an ideal gas is given by that same Boltzmann constant times the temperature times the number of atoms in this gas. Most gases are not ideal. There are all kinds of subtleties here, but the essence of what we see here is the temperature is a measure of the random motion of the atoms, and that the pressure and the volume increase with rising temperature. Now, if you take a gas and you cool it at sufficiently low temperatures, and if the pressure is sufficiently high, we'll see that later, you form a liquid phase, which is similar to a gas in that it doesn't have a fixed shape. The atoms are moving around, but they're weakly bound. And as a result, you form a phase called a liquid, which is almost incompressible, which means under reasonable pressures, it maintains a constant density. The volume of a chunk of a given amount of liquid is pretty much fixed. In both cases, in both phases, the density decreases with temperature. What that is especially useful to us for is it tells us that if you have a collection of fluid under gravity, then the warm fluid, which is expanded and is therefore less dense, will rise because it floats above the cooler liquid. And this brings us to the point that in equilibrium with gravity, the pressure in a collection of fluid will not be constant and the same at all points on the container. This is the case in the absence of external forces. In the presence of an external force like gravity, pressure will in fact increase with depth at a rate proportional to the density of the fluid. And let's see a demonstration of this, and maybe it'll help us understand what's going on. In this image, what we see is very simply me holding a slinky, a spring. And what you see when you look at it is the following not very surprising fact, which is that near the top of the spring is more stretched than it is near the bottom. And the way you understand that is quite simple. A slinky stretches more the more you pull it, and the top half of the slinky is holding up its own weight, as well as the entire half weight of the bottom half of the slinky, whereas the coils of the slinky very near the bottom are not holding up anything, and so they're relatively relaxed and unstretched. The higher up the slinky you go, the more of the weight the slinky is supporting, and therefore, if you look at it carefully, you'll see that the degree to which the slinky is stretched decreases uniformly from top to bottom. What we see here is me holding a cup of water. Now, this is to demonstrate the decrease in pressure with height or increase in pressure with depth. Now, this is true for the air. We know that at high altitude, air pressure decreases, but remember, the decrease in pressure is due to the extra weight of the air, and since air is not very dense, we're going to assume that air pressure is the same everywhere in this room. Not so for the cup, because the density of water is much larger. The water at the bottom of the cup, just like the spring at the top of the slinky, is holding up all of the water above it, whereas the water at the top of the cup is not holding up anything. And so I expect the pressure to increase from the top of the cup towards the bottom, respectful of the density of the water in the cup. And there's a way to see this. The way you see this is we drilled holes in the edge of the cup, and when I open those holes, if the pressure in the fluid is identical to the pressure at the top, which is the pressure of the air around it, then the fluid will happily stay in the cup held in by air pressure. But of course it won't. When I remove my fingers, the fluid will come splashing out, impelled by the excess pressure at the bottom of the cup relative to the air pressure, which is similar to the pressure at the top of the cup. And in case you're not certain that this is due to the weight of the water and to gravity, I will drop the cup, at which point fluid becomes weightless. The pressure at the top of the cup and at the bottom of the cup are now the same, and indeed the fountain ceases. So I hope I've convinced you that in a fluid in equilibrium under the influence of gravity, pressure increases with depth, depending on the density of the fluid. This is going to be important in astronomical context in understanding the structure of things like planets and stars, which contain fluid and are certainly held together by gravity. We talked about gases and liquids. Matter comes in a solid state. In the solid, the positions of atoms are roughly fixed. They can oscillate about those positions. This allows a solid to maintain its shape under external force. You can apply pressures and stresses, and a solid will react, but only a little bit. It will not, in fact, change its shape to suit a container. The slinky we had was a very good example of a solid object. It deformed in response to gravity, but it didn't completely stretch out. It gave some small proportionate response to the stresses that were placed upon it, and the larger those stresses, the larger the response, but the response was limited. The slinky retained, fundamentally, its shape even under duress. In all of these phases, fundamentally the interaction is between each atom or molecule and those near to it. There is no long-distance interaction or there's a weak interaction between atoms on one side of the slinky and on the other. Each bit of the slinky knows about the bits around it, and the result is that if you, for example, compress the slinky at one point, or move it at one point, then the perturbation travels through the material as each piece communicates the information, if you wish, to the next bit over, and these mechanical deformations of a solid, a liquid, or a gas are called sound waves, and they travel with a speed characteristic of the material. Now, the most familiar to us, of course, are the longitudinal sound waves in air. That is what we hear with our ears. But let's use that slinky as a very nice demonstration of wave propagation. To do that, let's see what happens when I let go of the top of the slinky. Remember, the slinky was extended in such a way that it was in equilibrium. The net force on every bit of it vanished, and this had to do with the fact that it was more extended at the top and less at the bottom, so that this compensated for the pull of gravity on every individual piece. Now, when I release the top of the slinky starts falling down, but near the bottom everything is still in equilibrium. The bottom of the slinky is not falling. What we see is a density wave propagating at the appropriate speed determined by the slinky through the slinky, and it is only when this wave reaches the bottom of the slinky that the bottom begins actually to fall. Until that time, it is in equilibrium, and the information that something has happened at the top has not reached it. What we're seeing is a sound wave. You bang on something at one point, and it takes time for that deformation to propagate through the material and reach the other end.